Okay, hello everybody and welcome. Welcome to my talk. I'm going to give you a quick outline. I'm going to make an introduction. I'm going to reprise the birthday problem, quantify Dinosaur Pee as promised, discuss some floating point values, and answer 4 questions. So, who am I? My name is John Lakos. I work at Bloomberg in New York City. I active at the C++ Standards Committee, written a few books, which I'm going to mention here, and they're very relevant, but not to this talk. These are software architecture. A recent book that we just came out with, which was a collaboration from all over the world, is Embracing Modern C++. It's available now. It's got an amazing amount of information about C++ 11 and 14. And if you're a C++ 03 programmer and you're interested in learning the new features of 11 and 14 from engineers after 7 to 10 years experience using them, this is your book. It's designed specifically to be modular and approachable on a feature-by-feature basis. But I'm not talking about that. I'm working on some other books, one with allocators and Josh Byrne. That actually has an ISBN number already. Practical contract-driven development, that's going to be a little bit later. I'm currently working on another one, Embracing Modern C++, I'm working on and preparing for it, but that's going to be coming out even later. That's the next edition of the EMC book that's going to cover C++ 17. And finally, I started this book before I published Large Scale C++ Volume 1. And I'm published, the next one I'm going to publish is Volume 3, and this is about verification and testing. And in fact, this talk discussed the birthday problem in it in 1999. I still haven't published it yet, but it's almost completely written, believe it or not. So anyway, we're going to talk about the birthday problem as it was known in 1999, and it comes from that. Anyway, the third volume covers things like component level testing, test data selection methods, test case implementation techniques, and test case ordering. We're going to focus on boundary conditions here, which I'm about to explain, ad hoc boundary, area testing. These are all different kinds of testing, data selection methods. There's a really fascinating one. The depth-ordered enumeration happens to be my favorite, and it's great for testing containers. But that's not the topic of this talk. The topic of this talk is really a special case of boundary conditions. So I'm going to start talking about that right now. There are at least 3 kinds of boundary conditions: those that are defined by the interface, created by the implementation, and imposed by the platform. You guys probably do recall the birthday problem. I'm not going to repeat it. I'm going to say it a little more carefully here. I'm going to read this one. What's the minimum number of people we would need in a room for the probability that at least 2 of them have the same birthday is greater than 50%? So that's a mouthful. And we have some simplifying assumptions. Only the day of the year matter, there are 365 days in a year, no leap year. Birthdays are uniformly distributed over the days in the year. And the question is, how does the probability vary with the number of people in the room? So that there's a little bit of a different kind of birthday problem, if you will. I'm going to ask us to write birthday function. And I want a little bit of interaction from the audience. I will tell you that as much as I've been working on this talk for a long time, I finished it about an hour ago, and I got 2 hours sleep last night, and I worked almost 20 hours straight. And when I started, I was almost done. So I can't even. You would think I would learn by this time. Anyway, so let's design a function that provides a probability value in the range of 0 to 1, as a function of the number of people in the room. So I'd like you to help me design this. So we have to go quickly. I can't spend a lot of time on this, but I want a little bit of head nodding and agreement or disagreement if you disagree with me. What's the interface look like? The function name. What does it return? What are the parameter names and types? Think about it. This is an interactive thing. It's a very interactive talk because you're being held captive here, and I want to really see if I can impart some knowledge I've learned over the past 18 months here since I wrote a book on it. Oh, my Lord. What is it? What is the contract? What does it do? How wide should we make it? Wide, narrow. These are things about contracts. Wide contracts don't have preconditions. What's the essential behavior? What are we expecting if we satisfy the preconditions? What do we expect it to do? What are the conditions under which the function's behavior is undefined? These are all things we have to think about. So anyway, let's go ahead and try to define this thing, the birthday function. What's the name of the birthday function? Somebody. Birthday, a little bit better.
Probability of same birthday?
I heard same birthday, sold. Same birthday? All good? Okay. What are the arguments? The parameter type and the name. Somebody. Somebody said unsigned. I'm not a big fan of unsigned when we're talking about the integer domain, but that's another topic. Let's say we go with a vocabulary type. What's the basic type? I realize it's not going to be negative. I realize it's not going to be greater than 65. I don't want to pass in a short. I don't want to do that. So let's just pick a vocabulary type that we use in C++. What is it? I heard int. I'm steering this a little bit. What's the name of the argument? I'll take it. So far, so good. I'm hearing it in the audience, right? What's the return type? Great. We're all on the same page. So this should be easy, right? I couldn't go wrong, right? Not a problem. Every one of you in this audience could do this, right? You can make this work. Oh boy. Return the probability that at least two of the specified randomly chosen num people were born on the same day of the same month. People born on February 29th are excluded. The behavior is undefined unless 0 less than or equal to num people. So it's specifically saying that if you give me -1, I'll do whatever I want. If you give me any non-negative number, it's okay. I'll give you an answer. Make sense? Okay. So here's some math. I'm going to do this a lot. When I have math and I don't want you to look at the math, I'm going to just put it on the slide for a second so the people at home can look at it for all day. But I'm not going to bore you. There's going to be more tables in this talk than you've ever seen in a talk. Don't look at them for more than a half a second. You can catch the video. Try to get the message from the in-person talk, then go to the video. Okay, that's my suggestion. For you, those of you at home, when I click through something quickly, you just stop on it and look at it as long as you want. Okay, so this is basically the mental model that I had of this function before I wrote it. Basically, it starts up, it looks something like this. So I wrote it in ASCII because that's how I write comments when I'm writing code. I draw these nice pictures and whatever. And so I'm going to use this, this way of testing. This assert is just a macro. It's just the way that I write test drivers. Please don't get all worried about what kind of test framework I use. Assert means this is true in whatever framework you like. And I say that these things are true. These are not values. The first two are values, but the third one is a property. It says this is true. And I think we'd all agree that if you get two people in a room, the probability that they have the same birthday is non-zero. We good with that? Okay. And if we have, if it's 365, the probability is less than 1 because it's possible we could get 365 people in a room and not have the same birthday, albeit unlikely. But if we get 366, no. 367, no. So these are boundary conditions. We're just going to test the boundary conditions just to quickly make sure that we haven't written complete garbage. And so these are external interface boundaries. We're going to check int max, also platform boundaries, and we have an assertion failure. Oh my goodness, what happened? Yes?
Your interface said less than or equal to 0 was undefined, so I don't think you can have that versus unless the comment is on.
What did I say?
It was less than or equal to 0, not less than 0.
Okay, so the comment is? Oh, in the previous slide. Thank you. This is very good. So let me just go back. Hold on a second. In the previous slide. Excellent. One more. Here?
Wherever you define the function.
Here.
Yeah.
The behavior is undefined unless 0 less than or equal to num people. We're good. Okay, if you find a bug like that, I want to hear about it. I'm going to answer questions at the end if I possibly can get through this. We'll see. There's more than 200 slides in this talk, just be warned. So we saw that. I'm just going to get back to where we were, remind everybody. And I think that could be taken out in the videotape if we need to, or we can keep it. So let's go to the next one. This was a failure. What happened? Why is this a problem? Does anybody know why this is a problem? Okay, good. So here's the birthday function. This is about what it looks like. If you were to graph it, if you had, huge infinite precision numbers and all that. And you get something that looks like this in the beginning, 0, 1, 2, and then you get this in the end. 367, good, good. So what happened? This is bad. And We tried 364, it's bad too. And 363 is bad. But 98 is good, 99, 100, 101, 102, 103. What are we gonna start to do, anybody? Binary search? Problem, it's good. It works for 183, doesn't work for 184. 183, good, 184, bad. So, that's good, that's bad. Right here, everything to the right of 183 is 1, exactly 1. Why? Do we have a bug in our code? What's wrong with our implementation? There are not enough doubles. We got to get some more doubles. Absolutely, I'm with you. Watch this, I think you're on the right track. So assert 0 less than num people, because this is a precondition and we want to make sure that people don't call us with things we never promised. And then we're going to say if it's larger than 365, we're done. That's an early exit condition. We normally put a return comment all the way on the right side, I forgot. Then slideware. Then double probability equals 0. This is how we start our collection. This is our accumulator. And then we're going to have a for loop. And then we're going to write some code that probably is right, maybe not, I don't know. And then we're going to return the probability. So you could imagine a function like this might work. I'm not asking you to check it now, but please feel free to check it at home. Please go ahead and test that function. Now, we've encountered a platform boundary between 183 and 184 people, okay? Using double to represent almost 1. Okay, so IEEE 754 is what we're going to use, and excuse me, and this is the bit pattern. I want you to look at this very carefully. The first bit is the sign bit. The next 11, this is for a double. The next 11 bits is for the exponent, and the next 52 bits is for the mantissa, and that's what it looks like. And so, okay, I just remembered I'm gonna have to give Parsa something in just a second. So Parsa, if you wanna come up here and I'll give you the answer on the side. So anyway, this is the bit pattern for 1, exactly. So pardon me for a second. My sincere apologies. Thanks. Sorry about that. All righty, that's for later. All right, anyway, okay, so what we're looking at here is the value of the exponent, and this is the closest number that we can get to 1, and that's that. And then we have this, and that's the closest, that is 1. So that's how much room we have, and if you notice, we're using the full mantissa. So even though this isn't a denormalized number, if you will, when you get to getting close to 1, you're actually trading off significance for being close to 1. The closer you get to 1, the less precise, the less number of bits you have to play around with. So that's the problem about getting close to 1. Now, if you look at a 0, it's completely different, completely night and day. So if you look at the 0 pattern, I can get very, 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 very close to 0. And in fact, without losing any precision, I can do that. So if you look at this, this is 0. Look how close that number is to 0. The difference between 0 and that, and a little bit bigger than 0, is very small compared to the difference between 1 and almost 1. That's the takeaway. That's the starting takeaway before we get to doing the quantifying part. So if you understand this, you're halfway there. But there's more. So how can we fix the birthday problem? We cannot fix it. What should we do? We should rework our interface and contract. How? Use what we just learned. So when this kind of thing happens, be alert to it. Say, ask not same birthday, ask unique birthday. That was the only mistake. We misnamed our function. We should have named it unique birthday. So we can express the probability that no 2 people have the same birthday like this. And then we can use Stirling's approximation to see if the number that we're going to get is going to be in a reasonable range. That number is about 10 to the minus 157. and that's going to be a lot greater than the resolution we have with the double to get close to 0. So we're going to have those nice mathematical properties we want as we approach 0, whereas when we approach 1, we'll pin at 184. Does that make sense? You with me? So that's the thing you want to understand for the rest of the talk. And I will promise you there's going to be more math. So all I did was just change at least to no. Literally change the contract like that. That's it. And if you want to get your number, find a very big floating point number to subtract 1 from, if you will. So we're looking at this. Here's the change. Here's the problem. We have 1 minus the probability. Let's kill that. We just killed it right now. And all the blue is the changes we made to the code. We get rid of this, and here's our program. Very little change. We changed the name. We didn't change the signature. We didn't change the return type. We changed the contract. That's it. Awesome. So now we've got this, and I'm not going to belabor the point. So I'm going through these things quickly as I'm known to do. This all works. Unique birthday, yes, yes. Problem solved. And we're moving on. That took a little longer than I hoped, but the observations I want to just say is we don't always know what we're looking for when we start out. We want to try to figure out if what we're doing is about right. So we do some little quick tests to see if they are. If we create these thoughtful tests at the interface boundaries, or we might catch interface bugs, and also platform bugs, just by giving it a shot, just trying the ends. If the ends are right, about right, the middle is often right. Not always, but it's a good sign. Thorough testing does not necessarily tell us how to solve a problem. It does, however, alert us to when we haven't done so yet. So testing will inform you. And I cannot tell you how many times I thought I was done, and now I start testing. Oh, I'm not done. Oh, no. All right. Second part of the talk. Combinatorics is fun, right? Main topic of the day, how much of the world's water is Dinosaur Pee? This is a pressing question that I'm sure you all needed to know or you wouldn't be here. So, how did the topic come up? Meet my stepdaughter, Ava. Ava came into a movie. I was sitting with my wife and announced from the internet some very positive statements about how much of the world's water was Dinosaur Pee. And in fact, had very good reason to believe that those statements were true. And in the internet, it's on the internet, it must be true. And who am I? I mean, it's on the internet, you know? Okay, so some considerations. Many dinosaurs peeing. Many liters of water on the earth. Many millions of years peeing. Many molecules in a liter of water. Could it be that every molecule of water on the earth is tainted? What's the probability of that? Think about that. What's the probability that every molecule on this planet was once inside a dinosaur? Okay. What's your intuition? So here, I came up with 4 questions. This is for you at home, guys. Assume that all dinosaurs have equal access to water. So in other words, a spherical ocean and a spherical dinosaur population superimposed. What proportion of the Earth's water is dinosaur pee? 0, almost 0, some, almost 1, or 1? What is the probability that all molecules of water on Earth were once inside a dinosaur? Again, 0, almost 0, somewhere in the middle, almost 1, and 1. Okay? Suppose the expected amount of untainted water turns out to be on the order of a single molecule of water. What would be the probability that all the molecules were tainted? This is conditional probability on top of a lot of math. So think about that one. That is a ridiculously cool answer, like most puzzles. And you can use this as an interview question if you like. But you won't. And the fourth one is, it's the same answer set. And the fourth one is, if I have an 8-ounce glass of water, and I have lots, this is way more than an 8-ounce glass of water. This is supposed to be a 20-ounce cup, and I'm so thirsty. Props. Anyway, what's the probability that I didn't just drink some pee? Okay. Same answers. Okay, now's the chance. We're going to do a recap. Throughout this talk, I want you to be thinking about the answers to these questions because this will make you a better programmer. Promise. Record your answers in your mind somewhere, but don't lie, don't cheat. Don't cheat yourself because I'm not going to know. Just know what you said and then think about what the real answers are and why. What fraction of the water is dinosaur pee? What is the chance that every molecule is pee? What would the answer to 2 be if 1 were all but 1 molecule? And what's the chance that my cup of water or coffee is pure? Okay, wait, we had to wait because I was working on this book. And finally, I got it done, but I was just chomping at the bit to get the information. Over time, I accumulated some facts. The facts don't matter. They matter a little bit. The point is the math matters, and we'll go get the facts. Except how would you know how much dinosaur pee there was per day, 100 million years ago? Who knows? But there are some ways to calculate it. So it's an open question. And finally, I was done with the book. And I used some simplifying assumptions as we talked about. I made a wild-ass guess that the dinosaur mass was approximately equal to the mass of animals on Earth today. I found out how much the typical reptile pees per unit kilogram. And then I did some multiplication. And I came up with some answers. And this is just a wild-ass guess. That's what I got. If you think it's something different, you're fine. But the point is you have an order of magnitude at least. You have something, a rough idea, something that might possibly be reasonable, okay? So recall the differential equations. We've all done differential equations. And believe it or not, I gave this talk twice as a lightning talk. And I didn't finish the first time. I got to the second to last slide and they yanked me. But if you're interested in a really good talk, C++ Now, I actually made it through all the slides in 5 minutes. So if you want to see a really entertaining talk and you want to see someone who had a crippled thumb right afterwards. Okay. So here's some math. We're not going to look at it very long. You know this. You've heard it. You were in freshman calculus. We're done. Okay? That's total water. Y0 is total water. We multiply it by a fraction. We get the remaining total pure water. Okay? That's it. That's what it looks like. What are we talking about? We have an instantaneous rate. It's an exponential decay, and we're talking about not how much water is P, but how much water isn't P. How much water is pure? How much water is P? How much water is pure? We've seen this movie, right? One is better than the other. So we can derive the rate pretty simply. We have that instantaneous rate. We get this rate. There's some facts. We're not going to worry about them. Plug in R and T, and here we're going to get some answers, some real answers. Here we go. You ready for the answer to the first question? And, so what's the answer to the first question, do you think? Don't say it. Okay, say it. Do we think it's D? Do we think it's almost all water is dinosaur pee? Because 3% is pure? Anyway, I thought it was a good idea. What if we use daily rate instead of annual rate? Does that matter? Here's the daily rate. Now, all we did was just do a little multiplication, and it turns out when you use an exponential and continuous compounding, it doesn't matter at all. No worries. Make it compound by minute if you like. Doesn't matter. Doesn't matter at all. No difference. They cancel. Okay, that's not a problem. How about discrete probability? Let's try it again. Try it with discrete probability, because I want to be sure. Because I'm telling you, my daughter Ava is hard to convince. So, what is the fractional rate of decay? Okay, that's R. Y is the quantity of pure water. And Y0 is the initial water. And now we've got finite time units. And you'll notice this is interesting. Why is this true? Well, it has to do with something called compounding, but it all comes from this kind of stuff. But we're not going to talk about this kind of stuff. It's too much for this time of the morning. So we'll talk about compounding shortly. As I said, I'm going to go through this stuff really quickly. I want you to pick up the high-level stuff. Go to the videotape for the detailed numbers because they are painful. And when I was looking at them this morning, I couldn't even tell what they meant. So it was, very bad. Remember, this is how much water is not P. How much water is not P? Okay? All right. So now you're going to see your first table. Who the heck knows what this table means? Well, there's a little thing in the lower left corner that keeps me sane. And it tells you what the time is, and it tells you what the rate is. And when I say ours, I mean what I came up with. So this is my time scale, and this is my rate. Okay, so that's what we're talking about. And so this is a specific thing that's happening. Okay, that over 165 million years. And you look at the the amount of water that we have that's pure in the continuous one and the discrete one. And you'll notice that it's not that far apart. And if you look at the difference, it is the actual difference, and we define difference underneath because errors and differences and everything, people say this is the error and you don't have any idea what they mean. It really can be a problem. So if you ever describe error, please say what you mean by error or difference. So we're noting it. This is how much water is pure. So I just want to emphasize every number that you see that looks like it's talking about water or P, it's talking about water, okay? Even though the question is how much of the world's water is Dinosaur Pee. Now, compound interest, you've all seen this. The K is the compounding factor. So even though the interest rate is expressed annually, we might compound, say, daily. I was asked to put this in because Bloomberg is a financial services organization, and they would be very upset if I misled you and didn't talk about the APR, annual percentage rate, equivalent, whatever. Oh my Lord. Anyway, consider yourselves on notice that the APR is not going to be the same as the compounding interest rate, okay? Just know that. The compounding rate will be a little lower, but it'll compound. It'll be good. So, all right. So, let T to the years, R is the fractional decay, and Y is the quantity of pure water in liters, and let K be the compounding factor, and look what we've got. Now let's find out how much that hurts us. So now what we're talking about is compounding per day, per year, per 10 years, per 100 years. What you'll find is very interesting in this slide, which is using our data, is that until you start compounding with million-year intervals, you're doing okay. In fact, if you compound with millennium, you've got 0.3% error. Error is defined below. So that's kind of cool, right? So compounding discrete probability is not a problem. Okay? And if you have an infinite precision computer, you're going to want to use the most accurate, the smallest increment because it's the best approximation. Other attempts at this problem. I watched a truly great video on this subject by Inquirity. And I say this because when I'm really late at night, I say inquiry, and then I have to say inquirity, severity. It's my own thing. I'm working on it. Anyway, Inquirity. Here is the URL where you can find it. I strongly recommend you watch it. It's delightful. It's absolutely delightful. You're going to get a taste for it today because I couldn't resist. So here it is, drinking Dinosaur Pee. And here's the guy, and he's going to talk to you about combinatorics. And he did this himself. He invented his own way of calculating Dinosaur Pee. It's fantastic. He did it himself. This is like a completely different way. No one has ever seen this way before. It's not quite true. But it's the best thing on the internet, and it's really well produced. So this will explain to you something that's very important. If you're not very familiar with it, expected value is a weird thing. How does expected value differ from a probability density function? I'm sure you think about this all the time and go, John, go away. I know that. Anyway, this will help. So the water going out is water being consumed, and the yellow marbles going in is the replacement of Dinosaur Pee molecules. Just imagine it that way. And so we start out with a certain number of molecules, and we're going to pull one from there, and there's not much surprise. The first time you do it, are we going to get yellow? No, because there aren't any yellow ones in there. That's not a surprise. You get one marble, put it back. It's pretty easy. Now there's a 10% chance of getting a marble. And people are comfortable with that because there's one yellow marble and 9 other marbles, 10%, that works out great. Expected value is 10%. We're all very comfortable with this. And then trial 1, we get this. And now we have to do some math, and we say, well, it's conditional this and this. And when we multiply it out and add it together, what do we get? We get, in the denominator, we get 100, and believe it or not, it's 19%. You go, what? We're going to get either a yellow marble or a blue marble. We're not going to get, 19% of a yellow. What is this? This crazy talk. But that's what expected value means. And it's very interesting to get your mind around expected value when you're dealing with molecules. At least it is for me. Then this happens again. This guy was amazing. He went and did it until he convinced himself that there was a series. It was awesome. So he actually looked at the series and numerically determined what the equation was. I was like, awesome. This deserves extra credit. If I were giving a course in this stuff, he would definitely get extra credit because of the method. But anyway, a lot of thought went into this. I just want to say that I added this. This wasn't in the original talk because I needed to know what they were. Anyway, deriving the geometric sum formula. I took his formula and I plugged in what he had so that we got something that we could actually understand. And this is what he had in his slides. So when you're looking at his slides, if you want to have this as a crib sheet, you'll know what's going on. He did this. And then, does everybody know how to sum a finite or infinite series? You could do that in your sleep, right? It's one of my favorite things to do. It's so much fun, I'm going to do it in 3 seconds. Here's a sum. Here's r times the sum. Subtract r times the sum from the sum. Cancel. Now you have this. Now you divide by the other and you're done. How fun is that? Come on. Yay. So this is summing a series. Not a big deal, but I just love to do it. Now plugging in inquiry symbols. So here are inquiry symbols in the geometric formula, and we get this crazy thing. This is a pretty complicated expression, and it will turn out that we're going to visit this a little bit later after we learn a little bit more about floating point numbers. So anyway, they have different data. Our data looks kind of like this. Their data looks kind of like this. What's going on? Well, they use alternative facts, and I put alternative facts in quotes because it's cute, because they came up with different ideas of how they'll model it. First, they used a different time scale. We use this, they use that. So there's about a 10% difference. That's cool. So on the time scale, we're varying it by 10%. So if we look at on our time scale, and what do we get? Now we're looking at different compounding units per day, per week, whatever, and we're using their time scale, but our data. So we're tweaking one of the dimensions and seeing what happens. And when we do that, we see that the expected amount of water is on the order of 2%. And that's, okay. You can just look at it right there. And the compounding doesn't matter. If we try to compare the difference between continuous and discrete for different time intervals, we'll see that the error difference actually goes down the further you go. So that's interesting information. But they used a bird model. Now I've got to tell you got to see the video to see how he calculated this. I couldn't. But anyway, he used a lot of interesting thoughts. But the point is that our P rate is this, and his P rate is that. Their P rate is that. And I say there because it's Inquirity, the company, and he is the guy that did the slides, just to clear that up. So I kind of mix them up a little bit. But anyway, it's about 10 times more. So now we're looking at a matrix that varies in one dimension, time, by 10%, and in the other dimension, rate, by an order of magnitude. This is an interesting experiment. Let's look at this. Let's poke it and see what's going on. So deriving the daily rate, they did the obvious stuff. They came up with the rate. And we're going to talk about rate as annual rate. If we're going to talk about daily rate, then it'll be compounded daily. We'll get to that. So here's another example. And the compounding here you can see, and this is using their data completely. They're using their time scale, and we're using their data. And when you take both, the longer time scale and 10 times the rate, you will see that the amount of water we have left over is a tiny number. Look at that number. If we go if we go per day, if we go continuously, it's like 10 to the minus 20th, order 10 to the minus 20th. And we don't get substantial errors until we start compounding by, let's say, somewhere around between 100 and 1,000 years. Interesting stuff. Okay, that's enough. Now, using infinite precision with Inquirity's data, here's the compounding over different things, okay? And and notice that the best one is the first one, because with infinite precision, we're going to get, we want to have the smallest one. And if you use some infinite precision machine or arbitrary precision machine, obviously, the closer the compounding is to, the smaller it is, the better you're going to get an approximation to continuous compounding, which of course is the exponential I immediately reached for when I wanted to answer this problem. All right, so now this doesn't have a time scale, so we're looking over different time scales. The longer you run it, and again, you'll notice that the error or the difference rate goes down. I'm just putting this up there just so you guys can get an idea. Always consult the little yellow box that says whether we're using ours or theirs. This is a kind of crazy case where you're using their rate, but we're using our time scale. That's the fourth quadrant of the box. We'll see a box a little later so we know what's going on. But just to explain that, anyway, we get to here, and here are the numbers that he plugged in. Now, the way he did it is he didn't solve the equation that I solved up front. I like to solve the equation symbolically and then plug in the numbers. He was ready to go with this. And I was like, really? And then that's the point where he pulled this out of somewhere and said, let's use this instead. So he did it, and this is what we plugged into the calculator. This is what we plugged into a Google calculator, and that's the result we got. Take a look. This is the point that we were going to get to. What's going on? What is that? That's the percentage probability, the expected value after 186 million years using their rate, that all of the water, of the water on the planet, meaning that there's a little bit more pee on the planet than there is water. And that was a problem. And he goes on to try to solve the problem. But let's definitely try to understand what really happened, because there is something that happened here. So if you ever see a probability greater than 1, be warned, you're looking at what I'm talking about. The whole point of this talk is if you're looking at a probability greater than 1, then you've got it backwards. You should be looking at something that's close to 0 in this probably. What went wrong? So remember this? What part of this thing went nuts? Was it the A over 1 minus R? Was it the A divided by 100? In other words, he multiplied by 100%. Did that 100% somehow screw with our rounding? What about 1 minus R to the X? What's going on there? What about R to the X? Like, which of these did we have a problem with? If you're just looking at this stuff, would you know where there's numerical instability? Well, you should be looking for that, because when you get close to 1, bad things happen. If you really care. If you're close to 0, life is joyous. So let's look at this. So here's what I decided to do, just for fun. Let's look at this equation, and let's just take out some stuff. Let's take out the stuff on the right. Let's just look at this. Look at the number, it didn't change. That should be alarming. We all test programs, right? What happened? It was this before, now it's this. Nothing changed. Okay, let's get rid of that 100. So we get rid of the 100 by dividing by 100. Now it should just be 1. It's not 1, it's still the same number, just the decimal point moved. So the 100 isn't really doing anything except in maybe the very last significant bit, but it's not affecting. Don't be confused. This is not enough digits for a double to be worrying about rounding. We have more digits. We'll find out how many in a little bit. Then I said, let's look at the numerator. Let's just look at the numerator. What's that number? That number is exactly 1. Does that sound familiar? But if we look at just the bit that we're subtracting from 1, look at that number. That's on the order of 10 to the minus 20. Can we represent 1 minus 10 to the minus 20 using a double? What do you think? Anybody say yes? Anybody say no? It's 0 or 1, yes or no? You with it? Can a double do it, or we don't have enough doubles? Okay. Should be able to be done? Or no? Okay, we have a yes. We'll see. But the point of this talk, honestly, is to make you sure. If we use Wolfram Alpha, we get this. So that number, when we put the expression in the whole expression, we get a number that has 19 nines and then some significant digits. This is the correct answer. The probability is very, 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 not the probability, the expected value is very, 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 very small, but it's not 0. And what this is saying, the probability that Dinosaur Pee is there is very, 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 very large, but it's not 1. It's 9, and then this. So you need to know that. Anyway, Use the Google calculator the Google calculator employs a double. So we did this with a double, and you'll see that if you say y equals 1 minus x, you get this number. Then you say z equals 1 minus y, and you get this number. Look at this. When you divide those numbers, when you divide x by x prime, z is x prime, it's just 1 minus x, right? You get a number that's larger than 1. It happens to be precisely the same number. Now do you see what's going on? That 1 minus thing is biting. This equation has 3 of them in it. 3 of them, I tell you. Magical. So if you look at a float, you can't do this stuff. If you look at a double, it's the same as Google. If you look at a float 80, it gives you a better answer, but it's not accurate. Only a float 128 gives you an approximation to the correct answer. And I don't mean a closer approximation, I mean the other number is just wrong. It's not the closest double it's not the closest long double to what you want. That means it's wrong. It's just wrong. So think about that. So this will give you some intuition. Then I'm going to show you something that will make you blind. Don't look too closely, and then we'll move on. So suppose I say v is 10 to the minus 1. Is v approximately equal to 1 minus v? Here you go. Is that close enough? What about 10 to the minus 2? What about 10 to the minus 3? 10 to the minus 4? 10 to the minus 5? 10 to the minus 6, 10 to the minus 7? And 10 to the minus 8. And at this point, it's over. The double is 0. That's it. Or one, the mantissa is 0. You're done. You don't have anything anymore. So 1 minus v is 0, and it's over. So you've lost all your precision. So there's only so much you can do before you have to quit. We're going to talk about the floating point subtraction algorithm briefly. I'm going to just sketch it for you. You don't have to memorize this. There won't be a test at the end. We're going to what we'll do is we will increase the smaller number so that it lines up bitwise. We'll do the subtraction. Then we'll need to normalize it. Then we'll do a rounding, and the rounding may in fact cause us to have to normalize again if the rounding rounds up and we have to shift back one. I know it's a lot of detail, but I just want to let you know what's happening. So when you see it happen live here, this is what we start out with. We do the shifting. The thing keeps track of the bits internally in its 80-bit floating point unit. Then we do the subtraction, and then we do the normalization, and here's and then the rounding, and then we get the result. Okay, and so once we've done this, I can't even see it, it's so small. Oh, I can look at this one, that's much better. All right, so anyway, this is what we get. And the point is, we've done this, and this is what's happened with 1 minus 10 to the minus 1. Now, if you look at 1 minus 10 to the minus 2, you'll see this. You notice that a little bit more is happening. And I'm just going to show you that with 10 to the minus 3, a little bit more is happening. There's a lot more normalization going on to do the subtraction. And then when you do 10 to the minus 7, it takes 2 slides of normalization to get the thing shifted all the way over. So you're losing all those bits of precision. They're being shifted out. When you do the subtraction, you're getting only the highest order bits. And when you get to 10 to the minus 8th, it's over. You've shifted all your bits out. You don't have any more bits to subtract. Does that make sense? That's why it's true. Here's the answer at the end, and you're left with 0. So I'm just explaining the phenomena. I'm not asking you to recreate the floating point processor. However, if you go to the IEEE 754 specifications and the floating point processor manual, they will tell you in all great detail that these numbers are right, I think. Okay, so just to recap, if you look at a float, here's a nice chart that says the number of mantissa bits, the numbers it can represent, the number of digits you can reasonably expect. So in broad strokes, a float has 7 digits, double has 16, a long double has 20, and a float 128 has 34 decimal digits. So that's just a rough idea. Don't worry about the last digit. If you're worried about the last digit, you got bigger problems, but that gives you an idea of what your accuracy is going to be. So if you're using a float 128 and you're subtracting 10 to the minus 10th, that's only 10 digits. You still got plenty of digits left. But if you're subtracting 10 to the minus 50th, you're done, no matter which floating point type you're using. So again, we've got some more. Here's the example using a float 128. And you'll notice that the best solution, even with a limited, not an infinite precision hardware, is per day. Now, if we do a float 80, it's still per day. If we do it with a double, all using our data, it turns out that a year is better, and we happen to use years by just dumb luck, because we knew in our heart of hearts that a day and a year aren't going to make any difference with respect to compounding, because we work in the financial industry and we know that it works that way, and so it's good. And then if we look at float, it turns out that because it's a float, so if you're working on an embedded system, you want to have an even less precise thing, because less is more here, and you get that. So when we use inquiries data, their numbers are really close, and per day is best, per day is best. For double, per day is best. But for a float, again, 1,000 years is best. I just show you that just for fun. Now, remember this formula? We can make that a little simpler, because they could have canceled, but they didn't. So we're canceling there. And then we can do a little bit more. We can alternately say, we're going to represent it like this. If you get to this representation, the last one is a contract change, but it means that now you can get the answer with high precision. In the other one, you need either infinite precision or a float 128 or something to even make it work. So, how much water is plenty? They employed the discrete probability approach, and that's this one. How small is that? Is that too small? How small is this? Think about that. Houston, they had a problem. Recall this. Can't represent that as a double or a long double. However, you can represent 1 minus r as a double, as we have demonstrated. Okay. This is a very bad idea. Now, this is what they did. What if we do this? Look at that. That's a beautiful thing. And so finally we get to answer our first question. How much water is P? Now, if you look at this matrix, you'll see that in the upper left corner, we have a short time span and a less rate of decay. If you go to the right on the top, you'll see that we have slightly longer time span and a slightly less pure water. If you go to the lower left, you'll see that we have a high rate but a slightly shorter time span, and that looks like it's 3,070 liters in the world of pure water expected. And then the last one is, if we have both, the highest possible, we've got 17.6 liters of water in all the world. So that's the final answer there. Now, almost 100%, D is the final answer. Okay. To give you a feeling, we have only about 10 minutes left, including questions, so I'm going to give the rest of this talk at lightning speed. But that's okay, it was designed for that. You're going to laugh. Oh, sorry, I went a little fast. So this gives you an idea. 7.2 digits, 15.9 digits, 19.6 digits, 34.0 digits, just to give you an idea. And that little purple thing at the end is saying that's a shady bit. Not all of that bit, all of that digit is real. That's just to give you an idea. If you want to look at it visually, when you're close to zero, a float gives you that much precision. A double gives you that much precision. A long double gives you that much precision. And float 128 gives you the same precision in normalized form. But when you denormalize, you get that same little bit extra that you get around 1. So in addition to this humongous number of zeros, you get this little red thing at the end, which is the mantissa being shifted over. So in a denormalized form, you get that little extra red. And I did it graphically. It's not exact. If you go look, the digit at the end is not right. But you get the idea. Now, if you want to go check that number, you can. I promise you can actually find that I cheated. I'll go back and figure out what the actual last digit is, but I can't. Make sense? Visually, okay? What are the chances it's all P? What is the expected value? So we have to go into a little bit of discussion about expected value, but I'm just going to show you this without talking about it, because if I talk about it, I'll insult your intelligence. We all know this. Besides, I need a drink of coffee. Tell me if this makes sense. This is all superimposed. This is giving you the different, as you see, the expected value moves out, and it's a bell-shaped curve, and you have symmetry. So when you have a symmetric distribution, expected value can be very confusing, very, very surprising. What if we don't have a uniform distribution? Suppose I want to know the expected number of 0 bits at the end of a randomly chosen binary word. Just take a look at this. This is the expected value right here. And yet that's the distribution. Little less intuitive, right? But if you imagine, you put it on it's the midpoint. If you see what I'm saying, it's the average, if we want to say. It's the average of all the infinite possibilities that we might have. And they're not infinite, they're just the sum of all the finite events and their probability. So that's what it is. So now we know this is a fact, we're going to believe this fact. And we're going to say that there are about this many molecules, of 4.2 times 10 to the 46 molecules. We're going to do this stuff. Remember this? We're going to do some combinatorics, and we get this number. Look at the bottom. How many zeros? Look at that number. What machine would be able to represent that? You'd need 10 to the 44th zeros to describe it. Something tells me that that's a very small number, but it's not 0. If you notice there's an exponent in the exponent, that's always a bad sign. All right, so final answer, B. Next one, suppose, just suppose, I knew for a fact, it's conditional probability, that every single water molecule was in a dinosaur once, and we expect about 1 molecule's worth. Well, it turns out that the distribution looks like this, which is a little surprising. But if you get down to the atomic level, the probability of the first one and the probability of the second one are, for all intents and purposes, the same. The second one is an infinitesimal fraction larger than the first, and then it looks like this. So given that the first and the second are about the same at 1 over E, and the rest of it adds up to basically 1 minus 2 over E and a smidge, what do you think the answer is to question 3? Is it very, very close to 1? Is it very, very close to 0? What is 1 over E? Is it very, very close to 1? No. Is it very, very close to 0? No. It's somewhere in the middle. It's around a third. 1 over E. Final answer, near the middle. C. We got one more. What's the chance that this coffee has no P in it? Well, it's terribly small. And again, we've got, going back here, it's like 10 to the 25th zeros. So I'm drinking at least 1 molecule of P. Let's just face it. All right. So that's the final answer, B. How did you do? So we're going to, remember these questions? I'm going to answer them right now. First thing we know is nothing is 0 or 1 in this life. It's all physics. So if anybody put a 0 or a 1, you're wrong. No. Zip, zip. Unfortunately, that's what I was told. 100% probability, every single one. We don't care about polar ice caps. We don't care about meteors coming in and creating new water since the dinosaurs expired. It doesn't matter. It's 1. That's it. Well, no, it's not. So I did convince Ava, and she does believe me now. She's also very, very bright, National Merit Scholar winner, finished school without even trying in 3.5. She's really smart, very mathematically inclined. But anybody can, be lulled into a misconception if they read the internet and they don't think it through. This took me 1.5 years to convince. I just want to know, this is hard work. So that's the first answer, that's the second answer, that's the third answer, that's the fourth answer. Just the takeaways, and I'll have time for like 5 minutes of questions. You can read that. The big takeaway, though, which I actually came up with this morning in my delirium, 2x or 1 minus x? That is the question. And with that, I was eating in a steak restaurant, and this was advertised as Dinosaur Steak. And I'm done. I actually finished. I will take questions. And when we stop in 4 minutes and 21 seconds, I hope you stick around for a couple of minutes. I have some work to do. Okay. Any questions? Sir?
I think you said 1 minus x is usually x?
So I didn't use that terminology. I asked somebody to actually write that. And I said usually, because if you have infinite precision arithmetic, or if you're doing it symbolically, it's always x. But if you're doing it with a floating point number, it's not. And that's why I said usually, just to get someone like you to come up and keep me straight. Did I answer your question? You're very good. You're absolutely right. There's a smiley face there, by the way, I think. Any other questions? You're all good. So let me just find out. Did the idea of 1 minus x seem like a big deal when you came in? And does it seem like a bigger deal now? Do you get some appreciation for how it can really bite you if you're trying to do any kind of numerical calculation? The takeaway really is if you're doing probability and you've got something that looks like it might be very close to 1, reframe the question. Reframe it. Don't change the API, but reframe the question so that if somebody wants to say 1 with 256 bits of precision minus your number, it'll convert it, it'll subtract it, you'll be glorious, but it's on them to find that floating point type. Yeah.
Kind of along those lines, at the beginning you talked about using boundary condition or boundary checking as one way to validate your assumptions. Do you have any other kind of high-level tips like that for validating?
Well, yes, I do. If you look at chapter 8 of the book that isn't out yet and won't be out this year, you'll find that there are many methods for choosing test data selection. One of them is boundary conditions. We talked about just one specific case here. My man Vittorio, whose talk I did not go to because I was working on this talk, and I apologize to you profusely in front of everybody in the world. Vittorio, my co-author, is here. Let's give a hand for Vittorio. He wrote the book with me. And he's the source of much of that information. I learned from him. Go ahead, Vittorio.
First of all, I don't forgive you. You should know that. I actually have a serious question. You said to reframe, right? And reframe it as the opposite of the original question. But what if you actually want to display the information as it was originally conceived? You would still have the problem when you subtract at the end, right?
The problem is this. What Vittorio just said is, suppose you need to express that number. What you do is you give the person the bit, you've got 0 and 1, and you don't tell them what 1 minus it is, you tell them what it is, and let them find a type that has enough bits to represent it, or find a way, like I did with the zeros, or find a way to say it's this to the this to the this. Find a way to express it to a human being, because a computer isn't going to talk to you. It doesn't have that many, there aren't enough doubles.
So, practically speaking, could it be reasonable at that point to use infinite precision number?
Hey, if you've got it, but what if you're BDE, my company's source, and all they have is a double, they're returning a double. If all I got to do is return a double, a long double, maybe an N128, I'm gonna give you what you need with all the precision I can, and then you've got to go out and find that type. That's what I think.
Yeah, makes sense. Thank you.
But thank you for coming up, and again, I'm sorry, and you will forgive me eventually.
When will you have volume 2 of large-scale C++ out?
Okay, that is a wonderful question, and nobody knows the answer to that, least of all me. But the theory behind that is this. Honestly, architecture, I knew that probably before I was born, and testing, I knew that when I was about, 23. And then programming is continuing to evolve. And so I'm cheating. I've been alive a long time. I hope to live another 10, 15 years. And C++ will finally stabilize. And then I can finally tell you how to do it right in chat volume 2. But I can tell you today how to test it. So that's the answer. I wish I could tell you. But a more serious answer is probably not for 6 years. I have 8 seconds. Want to squeeze anything in, or are we done? Go ahead, quickly. Okay, the question is, the probability is really that close to 1, does it matter? That's up to the client. I just resent the idea of telling them it's 1 if it isn't. Great question. My time is up. Thank you all for coming. I had a great time giving the talk.